When you see recording is started, you can start. Yes, you can.
Okay, you started.
Yes.
So yesterday we have done all of those things on Excel, okay, like mean, mode, median, standard deviation, uncertainty analysis. So let's see how we can actually implement this in the physics experiments and wherever data is available. So let's start with the, there are two types of errors. One is random errors. Yeah, so random errors can be estimated. Okay, so but the systematic errors cannot be estimated. They have to be eliminated. How can you eliminate them? You can have different techniques of eliminating them. Suppose your graph, you are expecting it to pass through origin, it is not. You can investigate and see whether there is some systematic error in that. Okay, so systematic errors have to be eliminated. So there's no statistical way you can determine it. But random errors, yes, since they are random in nature, we can have different statistical tools to estimate them. Okay. So initially the approach of a measurement was to get the true value. Okay. So now the approach is not to get a true value, it is to estimate the true value, because you cannot, whatever you do, you will not be able to get a true value, because there is a limitation on your measuring instruments. Okay. So beyond that, you cannot. So it is better to estimate the true value. So when you're estimating the true value, now two additional things are required for that, is characterizing the range within which the true value lies. So your value which you have quoted is plus minus what? The true value. Okay. And the true value which you are saying is what is the level of confidence you're saying it is going to be within this. Okay. So sometimes the error in the reading is more, then also that thing works fine. But suppose it's a medical equipment or something. Okay. So there's no scope for much error. So there the confidence level of the estimated value, okay, and what range it will be, that has to be well known, and with what confidence you are quoting that, okay, this will work within this range. Okay, so the range of the value encompasses the true values. So the true value can be anywhere between that plus minus, that is what we expect, and specify the level of confidence. Okay, so whenever you write a result, okay, so x plus or minus u. Okay, so this is what we had found yesterday, the standard uncertainty we had calculated. This estimation, you can get it by multiplying some factors, or even if you use regression, this is already quoted when you get this regression, what is the confidence level. Okay, so regression normally gives, when you do regression, it normally gives you at the value of standard uncertainty at 95%. It does specify. So, okay. Any questions still here? So, what it is? So, I think I can go ahead. Now, there are types of how do you evaluate these uncertainties. Okay. So, there are type A and type B. I will not spend much time on type B because those are very special. What we'll be dealing is only type A, which are normal or the Gaussian distribution, as you know. We assume that the probability distribution function is Gaussian in this kind. Okay, I'm skip this. So the probabilistic approach using mathematics, that is the probability density function for type A is Gaussian, and the others, as you can see, are like, no, this is type A. The probability distribution function is your Gaussian distribution. Okay. Type B, you have rectangular and triangular distributions. Okay. Maybe in a problem, I'll just touch on one of them. So usually used in, so as a set of repeated and scattered readings. Okay. So the scattered, the distribution of the scatter is here. The probability density function is Gaussian. Okay. So when do you use this kind of thing is if you have an instrument whose error is, let's say, the same thing, it is not going to change, it's a calibration thing. Okay. So you can use this kind of functions. So we have done this yesterday. The standard uncertainty is your standard deviation by root n. Okay. So your 1u, because you write it as plus or minus, that's why it is 2 sigma they call, is 68%, or means if you give me a value or from a particular reading, so that will lie within the true range thing. It is 68 times it will. The remaining times it can go out of that true value range. Okay. So what do you mean by 2u? Means it is basically a 4 sigma. That is 95% confidence. Okay. So normally we stick to this because out of 100, if you're 95 times your reading lies, 95 times it lies within the true value range, it's a good estimate. Okay. And 6 sigma, which is 3u, is 99%. That means your value is 99 times going to be right. So maybe this would be required in the medical instrumentation field, where you would not like out of 100, 5 people losing their life because of some instrument. Okay, so people would go for 6 sigma. Okay, so standard uncertainty, we have done this. Okay, for this kind of distributions, okay, the standard uncertainty is different. Okay, and where A is the range. Okay, so it is the range of this. So if you take an instrument, so the calibration error, that would be the range of it. Okay, so if you take a scale like say plus or minus 0.1, so that is the range. So that would become your A here, and then you have this kind of distribution. Okay. Now this is for each this thing. Now suppose your function itself, okay, if your function is z, which is a sum of 2 other functions, let's say x and y, okay, then the combined uncertainty in x and y, okay, or if the function is even x minus y, it doesn't matter. Okay, the uncertainties are always going to get added up, they will never get subtracted. Okay, so the total standard uncertainty will be, okay, square root of, okay, the uncertainty in x square plus the uncertainty in y square. So this will give us the total standard uncertainty. If your function is not x plus y and it is x into y, okay, so in that case the relative uncertainty, okay, that is in z is uz, that by z will be the uncertainty in x divided by x the whole square plus the uncertainty in y divided by y the whole square. Now obviously you can multiply it with z once whatever you get the value, and you will get the total uncertainty. Even if it is multiplication division, the errors are going to get added up. Okay, and if it is a powered one, okay, then the uncertainty will be n times. So that's why when you do a specific experiment in a lab or something, and your teachers would say, okay, measure this more carefully, okay, or take a better least count instrument for this. The reason is that the error is going to get multiplied. Okay, if your function is x cubed, then it is going to be 3 times whatever is the uncertainty in x which you're going to. Okay, and then mixed we have this. So I'll skip this. Okay, so we'll discuss this problem and then we'll do this problem on Excel. When we can see I have done the calculation. The data is taken small, but if you have a huge data, then the amount of work you'll have to do is much large, and then using Excel functions, you see you can get your answers within minutes. Okay, so this is the reading. Okay, we have 5 readings, specimen thickness, and the reading for the hole depth. Okay, so you have to calculate the standard uncertainty due to the resolution of the dial gauge. Okay, so the instrument has its own resolution and therefore there is an uncertainty in that. Okay, you'll have to calculate the standard uncertainty due to repeatability of each measurement. Okay, and the combined uncertainty in 2 measurements, and obviously you'll have to give this combined of standard uncertainty and the level of confidence which we have. Okay, so let me just go to this. Now, if you look in this reading, how much is the least count? That is 0.2 mm. Okay, here I am using a triangular distribution for this. Okay, so for a single reading, okay, so that is A, that is my range, okay, divided by 2 root 6, and that gives me the standard uncertainty due to resolution of the dial. Okay, so since this is a single reading, I have used a triangular distribution. Okay, so normally in a lab we don't do this, but then the instrumentation uncertainty is also important. If it is negligible compared to your other uncertainties, you can neglect it, but if it is not, then you'll have to consider it. As we have done this, what we'll do is we'll take down these readings, okay, and find all these things from whatever we did from yesterday's this thing. Okay, so let me just copy down the data.
There is one question in the chat. What is the meaning of expanded in expanded uncertainty?
Yeah. So that is what I said. If I'm getting sigma, right? So if I want to make 4 sigma, then that is the expanded uncertainty. Okay. Now let me go here. So this is 1u. Okay. So this is the expanded uncertainty. So what we are calculating is this 1u. Okay, that is 2 sigma. So this is what you will get normally when you do the calculation, right? So the expanded uncertainty is you multiplied with 2 or you multiplied with 3 depending on your requirement. So that is the expanded uncertainty.
But sir, why we are like expanding it? Like what is the need of expanding the uncertainty as we want to minimize the uncertainty
Yeah, you have
in
already.
any measurement?
No, you don't want to.
Like,
You want to
I'm not
estimate
getting
it. No, you're estimating it. See, while doing the experiment, yeah, you will take all care that you will minimize it. But when you're calculating whatever is there, while calculation, you don't want to minimize. You will calculate what you're getting.
Yes.
So calculation, we are not minimizing. In fact, we are maximizing. That's what I said. Even the function is minus or whatever it is, we are always adding. Right? So we want to give a range where the true value would lie in between that range.
So in short, if we are expanding our range, then it is highly likely that we will get our true value.
Yeah, but at the end user would like to know, na? So for example, I said a medical equipment, right?
Yes.
Okay. So you would like to see out of 100 times, if I just quote this, okay, so 68 times it would be within that true value range. It can go outside that.
Okay.
Right? So when I'm using an instrument, I would like to see it is what is it is quoted with sigma, 2 sigma, 4 sigma, 6 sigma. Getting that?
Yes.
Okay. And so in calculations, we never want to underestimate anything. In fact, when we are doing the calculations, as we are adding them up, so you don't round off them here and here. Okay. You leave everything as it is, and whatever is the rounding off, we'll do at the end, not at each stage, because we are trying to maximize it only.
Okay.
Okay. Fine.
Yes. Thank you.
Yeah. So let us.
There is a question.
Yeah.
That why is standard uncertainty different from half of the least count, and how to get those formulas? And those formulas, I think, are given by statistical analysts. But
Yeah.
what is the physical interpretation of that? That standard uncertainty is different from half of least count.
You mean to say?
So
Suppose
when you use that, you use triangular distribution for
okay.
least count.
Yeah. So let us take an example that you're measuring some table length, right? Okay. And then you do the experiment with some tape or something, and then you say you're getting 70 centimeters. You did do it 10 times. Okay. Or you do it 20 times, and you're getting only 70 only as your answer. So what does that mean? If I use the Gaussian distribution function and calculate it, I'll get 0.
Yes, there is no deviation.
Yeah.
Right. So, but the uncertainty is not 0, that is for sure. So in such situations, we go with this kind of uncertainties, which are type B uncertainties. So, okay, Mahesh?
Okay, I mean that was the question in the chat. So yeah.
Yeah. So getting this, so I made a measurement with 20 times and I'm getting the same answer. Okay. And then you would say, okay, there is no uncertainty, it is 0. But that's not the case. Okay. So to handle such kind of situations, or mostly a single reading, so that 20, this thing will be taken as a single reading, and you will use this kind of distribution. Okay. So let us just maybe, okay, I wanted to do this. Okay, I have calculated this. But anyway, let's do it here. So this is our data, right? Okay. So what do we want to get? We want the mean. Okay, that's what I've done is I've used the traditional this thing formula and calculated, or as we have here, So this is 21.06, okay, 16.60. Oh, sorry.
Please use the same values instead of spending time on writing.
Yeah. So this I wanted to show. Now here I got 16.60. Yesterday we have discussed this. So what we'll do is right click on it. Okay. So format cells. Okay. So number 2, and now see it will show us this. Oh, why is it showing rupees? It was currency. Okay. So that was yesterday's. So we can copy this. Yes, such. Yes. So what we will do is we can straight away calculate the standard deviation. Now, this is a sample, right? Okay. So the sample here you can see that there are standard deviation of population and standard deviation of sample. So standard deviation of sample will have n minus 1, and when you take population it will be n. So this is a sample. So I will take, okay. So here also we can find the standard deviation. I'll increase the font size. Okay, 16. Okay. Now what we have to do? We have to calculate the standard. This is standard deviation, right? The standard uncertainty has to be calculated. Okay. So this will be equal to this divided by square root. You can say count. Okay. Here also you can do the same thing. Divided by square root.
I think you can paste the same formula because references are same.
Now I want to find out what is the total uncertainty. Okay. So for that, we'll have to look back here. Okay. So we have found, like, in the specimen thickness, we have found the standard uncertainty whole thickness, and there's an additional thing, that is the uncertainty in the resolution of the dial. Okay. Now when we do this, so this is 0.004, we have used the triangular distribution. Okay. Now you're using this dial for measurement of the specimen thickness as well as for the measurement of the hole depth. So this has to be 2 times okay, so the total standard uncertainty, okay, so will be equal to what? Square root of this value. Okay. Now what actually I should do here is, okay, before I do this, said it would have rounded off this values. Okay, so let me take all the values, maybe up to 8 or so. Here also this also would be the same. No, I could have taken more than this. As I said, I don't want to round it off at that stage. Okay, so this will be equal to square root then square of this plus this plus 2 times, okay, dial error, okay, that is which I have copied here. It's that. Wrong. Oh, sorry. Yeah, this is a mistake here. Okay. Yeah, I took this value, but the square of this and then under root of it. Okay, so this is the total standard uncertainty which we have. Okay.
Just 1 minute. Why are you adding up the thickness and the depth? I mean, does the question ask you to do that?
Yeah.
No, you will do this uncertainty provided you have added two quantities. In this case, is the question requiring that the thickness and the depth should be added?
No, I didn't get your question.
You are using a formula for the total uncertainty,
Yeah.
square root of thing del x squared plus del y squared,
Yes.
square root. Okay.
Yes.
That is true only when x and y have been added to get z. That is propagation of error. But
Yes.
here you are just simply talking about the depth and the thickness separately. There is no propagation here.
So maybe the problem doesn't mention that, but if there is a propagation error, then what do you do?
That's why I'm asking. Does the
Yeah.
question ask you that you do this, add
No,
it up?
that's my question is, if there is a this thing, then what is the total uncertainty in your this thing? Otherwise, separately we have calculated. Separately we have done the standard uncertainty in this and in this. I said if there is a propagation this thing, then the total standard uncertainty would be in your reading which you will be reporting is that.
I think read the question first. I think it will become clear then. What is the question looking for? The determination would require the depth of the hole to be measured and subtracted from the measured value. Okay. So it has to be either added or subtracted. Right. Carry on, please.
Okay, so this is the uncertainty in this, and then this would be the total uncertainty if there is a propagation error.
Sir,
Which is, yeah,
sir, why did we, sir, what is the third term here?
which one?
Sir, F11 square, 2 into F11 square. So why did
Yeah,
we
so
take that and what is that?
there's an uncertainty in your dial reading also. The least count of the dial is 0.022 that you can see from the reading. Okay, if you look carefully, okay, all your readings which are ending is even. There's not a single odd one. So the instrument least count is 0.02 and not 1. If you're assuming it to be a Gaussian distribution, then if it was so, then somewhere it would have come as 1 also. So, so the least count, that is 0.22. We are using a triangular distribution. Now, when you're using this instrument, okay, to make the measurement, so this uncertainty will also get added up because of the limitation of the instrument.
Okay, okay, sir.
Okay. As I said, if it is negligible, then obviously you can ignore it compared to your other readings, looking at your other readings. Okay, suppose if your uncertainty is like say 0.2 or something, and the instrument uncertainty is like say 0.002 or something. In that case, you can ignore it.
So
Okay,
when
sir.
you write the formula like that, wouldn't it multiply F11 and J10 and then add it to I10?
No, I didn't get you.
Like the way you've written the formula, right?
Yeah.
It's J10 squared plus F11 squared.
Hmm.
But then when you write it close to it like that, wouldn't it first multiply J10 and F11 and then add it to 10 square?
No, you look at the formula, how the propagation is there. Propagation error, as we said. Standard uncertainty in X plus the standard uncertainty in Y. If you have something else, standard uncertainty in the instrument, let's say P, then Q, and so on. It's okay?
Okay, got it.
Yeah. So so we have done this using this thing, and yeah. So here also you're getting the same thing. Now, what was the expanded uncertainty as we're asking, right? Okay. So now this is your total standard uncertainty. Okay. So this is nothing but when you write plus or minus as you report your uncertainty here, right? So what is the level of confidence? This is 68%. The expanded uncertainty is 2 times this, that which way it becomes 4 sigma. And when you report the final answer, whether you're reporting with this or you're reporting with this, you will need to specify. Okay. Example here, when I have reported here the final answer, the final value of the remaining thickness would be reported as this plus minus 0.053. So this is 0.053 is the expanded uncertainty which has a 95 level confidence. So whatever we get here plus minus, you multiply it with 2, okay, and then we round it off and then we report. Okay. few other problems. I'll put it in the assignment. Okay. Mahesh, anything you want? Anybody else has anything? Then we can move on to graphs. Yes.
Sir, can you explain why we multiplied 2 with the uncertainty of resolution in the formula?
Yeah. So the instrument uncertainty will be there when you're measuring the thickness, as well as it will be there when you're measuring the hole depth, right?
Okay.
Okay. So if you say only the thickness, what is the total uncertainty in the thickness, then this, okay, for that we'll write square of this plus your uncertainty in the dial. That's it, only once. But since you are using for two measurements, okay, so the errors are always progressive. They're going to get added up, and that's why 2.
Okay, sir, got it.
Okay. So if you're only taking a single reading, then yeah, this, the total standard uncertainty in the thickness would be this plus the dial error. Okay, there will no 2 will not come there. Okay, fine. What happened when this file was on? Okay, so let's come to plotting of graphs. Suppose we have this data x and y. Okay, then how do we plot this? Okay, now you go to insert. Okay, now you see that there's a line and there's a scatter. Okay, so let us plot both of that and see what is that you're expecting. There you go. Yeah. So let us take a blank graph. This is a line which I am saying. Okay. You can right click on it and then select data. Okay. Can add. Okay. So we can give some series name to it. Let's saying that XY. Sorry. One minute. What? Something wrong. So I just type, let's say, XY line.
You may click on right hand side and choose that.
Yeah.
Click on that right hand side blue box and now select the range. I think no, that should give you
Sorry.
2 columns.
Yeah, it should give me 2. That's what it is.
One column, only 1 column.
Okay, let me just take this. Oh, what happened? Sorry. Okay, so this is an XY, this thing. This is value is, okay, so this I have to, this is fine. Yeah, this value has to be.
I think the X values have to be deleted. Delete that. Now kindly delete the X values from the table.
Yes.
Now, X values are not 00110.
Yeah, yeah. Yeah. Okay, so this is what I have. This is, yeah. So what happened here was it was taking by default, as we said. So this is the horizontal x-axis. So it was taking 1, 2, 3, 5. So we edited this and give the x value range to it. And this is how an XY line graph would look like. Let us plot insert. Let us plot an XY scatter. Select data and okay. So this is your XY scatter graph. Okay, so here the X values, you select the X values, select the Y range. Now here you can see that these two are different graphs. So what we expect is this. Okay, so normally we don't use the line graph, but I just wanted to show you if somebody does a line graph, then what would happen. Okay, now we have this XY scattered, which is of interest to us. Okay, now here you see that there are no axes labeled. Okay, and so on. So click anywhere, so you will go back to your page. Now come back here and click on this chart area. Okay, then the design will pop up. Okay, so here you have chart layouts. You can have the font sizes, the chart layouts. Okay, you can have different layouts. So choose, let's choose this. So where we can have an axis title. Okay, so we can, this is very important when you're doing graphs in future also, because if you're sending your papers to some journal also, then all this needs to be properly labeled. Okay, now these are known as the grid lines. So the major grid lines for the y-axis, we have not shown any, or it is not showing any grid lines for the x-axis. So so you can select them. So you just click on any one of them, they get selected. There's a problem with my mouse. Yeah. Okay. Here you can see that format grid lines and format axis. Okay. So let me go to format axis and then I'll come to the grid lines. Now, this will be useful. Now it has taken, here you can see the minimum, maximum, major unit, minor units, okay, values in reverse order, logarithmic scale, display units. Okay, so if you want to display units, none, or you can just type the units here, it will display it here. Okay. Okay, maximum. Okay, let me just show you this. If I want the, see now the graph is starting from where? You can see it is starting from 0, 0. Okay. I want it to start from, let's say, 0.1. Okay, and let's see. You can see that it is starting from, not from 0, but this has become 0.1. Okay, now in this graph it is fine, but if you has a huge range of graph and you want to choose only a particular area of the graphs to be highlighted, and some of the area you don't want it to be, get rid of that, then you can change whether to start from 0, 0 or some fixed value, right? Suppose your readings are starting only from say 20 or 30, it will plot from, let's say, 0, 0. So if you're not interested in the intercept or so, then you can give this values, okay, the minimum values, okay, or the maximum values beyond which you don't want. Okay, now you can see here the major units is 0.1, okay, and the minor, so if I make it 0.05, so you can see that you have more, but this is not able to see. So that's how you can change this. Okay, 0.1. The other thing is you don't want this to be not there at all. You can delete them. So you will have only your data points to be shown. So similarly on the x-axis, you can format the axis, okay, on a similar lines. Okay, you can even change the alignments of the text and so on and so forth. Okay, so
Shekhar,
yeah.
because you are now talking about this formatting, Maybe this is a right point where you can also talk about which kind of formatting is accepted in those journals that you're talking about.
Yeah, I was going to talk at the end, but then Mahesh brought it up. Okay, now when you plot this graphs, okay, when you export graphs straight away to Word, then it actually compresses it and copies it to Word, which most of the journals don't accept it. Okay, you need to have minimum 300 PPI this thing resolution, so that when they print it, it doesn't. So when you copying this, okay, you can let's say I copy this and I want to paste it in some Word document. Okay, so you don't paste it directly like this. So you have the paste button here. Don't use this functions at all. You don't use even this. You have paste special. Okay, so here you have different formats. Okay, to be pasted. So you can choose a PNG file. Okay, and so and paste it. Okay, so even if by default your Word document has some resolution issues, then you can fix that. Okay, so but don't just copy paste it, so the resolution is lost. Okay, Mahesh? So anything else?
No, that's it.
Yeah. So now let me come to one problem which was interesting, and I was working with it for a long time, and then I had to do a lot of things, but I found an easy way to work around this. Okay, so here we have this data. I'll just do it, paste it down only. This is my data which is to be analyzed. Okay, let us take it away. This is,
Yeah, will you zoom in?
yeah, as now. So what here I want is the log of this, that is log to the base e. So I'll say ln, okay, of this value, and then I just drag, it will take the ln of all these values. Okay, now here this is experiment which is a heating rate. Okay, so the heating rates are 20, 40, 60, 80 and 100. Okay, so and this is the glass transition temperatures. So this is 827.00. Okay, it is, you know how to make it 00, and you should make it as a physics student. That otherwise it will tell us that the resolution of that was something different. Okay, so all of them. Okay, so what I need to actually plot is a graph of, okay, 1 divided by Tg minus Tg0, okay, which is a glass transition temperature at 0 degrees centigrade. Okay, so but I don't know this value. Okay, but I know that this data is a linear fit from the other calculations and so on. Okay, I'm pretty sure that this is a straight line graph which I should get. Okay, Now what do we do in such case? I don't know this value. Okay, so let me say I put a random value here. Let's say I put a value which is 830. Okay, so that is my TG0 which I am taking for the time being. Okay, and let me do the calculation for that. 1 divided by, okay, so this is the bracket minus that. Okay, since I know this is a straight line, okay, so the regression value for a straight line, okay, just I'll explain it here and then I'll, okay, so this regression value which is here, this r square, tells you this value can be between 0 and 1. Okay, 0 telling that it's not at all a fit, the fit is very bad. 1 saying that it is the best fit. So, but for all practical purposes, 0.99 is a good value where we can take it as 1. Okay, so r square, which is a regression value, tells me how best the line is fitted with those given data points. Is this clear? Okay, how to get this r square I'll tell you, but I was just telling what this is. So what is that I expect? I know it's a straight line, so that I expect that this value should be 1 for me, right?
So you are interested here in the in extrapolation. But at 0, what should be the value of TG, right?
So no, taking the TG value, I should doing an interpolation only, this best fit, not with TG0. So adjusting TG0, I should get a best fit for this this thing only, the same points which I have for TG. So the graph is 1 minus TG minus T0, okay, and ln beta, so for the same heating rate. So since I know that from the other calculations and so, that this graph should work out to be a straight line. Okay, so I'm using that information, and let's say we put this value to 1. Okay, so this regression value to 1. Okay.
So what you are meaning is you are assuming TG at 0 is say 830, which is your just
yeah, I'm
random seed
assuming
value.
this. Yes.
That is your random seed value, and
Random seed
ultimately
value.
you want after plotting the graph, you want regression
To be 1.
best possible as
Best possible regression, because I know that it is should be a straight line.
So this
if,
is your target. That 1 is your target to achieve.
Yes. So
Okay.
what when I achieve 1, so that value whichever comes would be my TG0. Okay, so let us plot a graph of this and see what we get here before we do the other calculations of it. With 830, let us plot a graph of this. So what will we do is insert an XY scatter. Okay, so right click on it, data select. Okay, add. Okay, so we'll give some name. That's it. Find PG0. Okay, so that's, so what is the X? Along the x-axis we have ln beta, that is the heating rate. Okay, and along the y-axis we have 1 minus.
Sir,
Yeah.
sir, in the y-axis, in the last four, apart from the first entry in the y-axis,
Yeah.
sir, in the formula we have to fix this F 23, right? I think it is not fixed.
Oh, sorry. Yeah, yeah. Yeah. Yes. Right. So we should put a
$sign.
$sign. Good. Now I think it's fixed, right? Yeah. Select data. Yes, access. Okay. So this is a graph which we are getting. Okay. Let's see. This is the graph. We have to take this graph to this. Okay. So how to go about? We'll have to label the axis. Okay.
Sir,
Yeah.
why there is so much difference between 20 and 43? Like at 20 it is minus 0.33 and
Yeah,
40 it is
because this is
0.24.
827, right? And this is 830.
But if it, that means for getting
All the
straight
other
line,
values, these are positive, right?
so in short, if to get the straight line, we have to neglect the 20, right?
No, the
You have to
point
neglect.
here is
The point here
if you
is
inspect,
we don't know this value exactly now, right?
inspect, a good guess probably could have been 820 or something like that. Okay, but he has purposely taken say 830. Take
Yeah.
probably wild guess. It is not even a wild guess. He had just randomly put a value.
It's okay. So I'm getting 4 points. The fifth point is going. So if you put, let's say, 820 also, then this. Right?
Okay.
So it doesn't matter. If you put 830, it will go negative. Okay. So what we'll do is next is what? We'll click on this chart area and then we'll select a chart type layout. So we'll select a layout. Okay. So that we can label the axes properly. Okay. So labeling axes is very, very important. Okay. So for that beta, we'll have to go to here, insert. Beta value. Yeah. Insert, close it. Okay. This axis The other thing what we need to look at the graphs properly is, okay, this legends, okay, what they denote, okay, but fine, here it has taken this same name, okay. We can change this if you want. You can change no, we want to add data labels, you can add so, okay. You don't want to add them, you can, okay. You can choose your data points and you can change the size of the data points also.
It will be in the format data series.
Okay.
Marker options.
Marker options. Here you have this is automatic now, built-in type. You can make them small, okay, or you can make them bigger, and so on. Okay, so you can change the size of the data point markers. Okay, you can change the color also, or the size, shape, whichever you want. Okay, so from here you can do that part of it. So, whether we want this grid lines or no, or we want the grid lines for this. Okay, add major grid lines, so it will add this grid lines. Okay, if you don't want, sometimes you don't want this grid lines, you remove this. If you don't want this also, you can remove this. Okay, so normally while making graphs, we don't put the grid lines on for sending some papers. Okay, unless sometimes you are interested in the intercept to be shown, so you can put those grid lines. Okay, or you want to find a particular value of intersections, and you can put those grid lines and then maybe remove that. So once we have this, then we have to right click it. We will add what is called as add a trend line. Okay, so add a trend line. When you come to a trend line, here you have options. Okay, exponential. So this, it seems to be with this value, the graph seems to be exponential, or we can have a linear fit. Okay, so algorithmic polynomial. Okay, so this polynomial 2, 3 fits in best, which it looks like, and so on. Okay, so let me just restrict my discussion to a linear thing. Okay, in case if you're sure that the intercept is to be 0, 0, then only you set this. Otherwise, you don't set this intercept to be 0, 0. Okay, you can display the equation on the chart. Okay, that's a linear equation. So this is the slope of it, and this is the intercept of it. And display the r square value on the chart. Okay, now you see that you're getting r square as 0.919. Okay, not very bad, but if you had taken 830, it would have been really bad because one of the point was just out. Okay, so is this clear?
Sir, I have one question.
Yeah, yeah, we can remove this part. Yeah, tell me. Yes.
Sir,
Hmm.
suppose I have done one experiment
Hmm.
and I have a complete set of data points or results, outcomes. I
Hmm.
don't know what is the formula, and I'm trying to find the formula by doing this type of curve fitting. Now it seems like it is a straight line. It
Okay.
also seems like it would be an exponential. And by
Yes.
doing so, I found that exponential fits the best.
Okay.
But in doing so, likewise, you say it was that exponential is also fitting, quadratic is also fitting, and then you shifted to straight line. So what made you decide that it is a straight line? Like I am totally new to these results, to this
Okay.
whole thing.
So now for that you will have to look what are the error bars in your graph. Okay. Okay. So if you're not really sure, then you will have to definitely look at what are the errors in your experiment, and you can actually plot those error graphs, which I'll do a bit later. So if you're confused, you can plot the error bars and see and whether your best fit line is within that error bars. Fine.
Okay.
So
So can
if
you
it
give
is
like
if it is within that, then obviously there's no point in going for an exponential or so, because your readings could have been anywhere in that range.
yes,
So Excel uses the standard deviation only to, or the least square fit method only to plot graphs. That's the algorithm they use for plotting graphs. So you will have to really look at your error bars. Okay, in that case.
okay.
Fine. Okay, now you see that this graph seems to be on one side and this values. So it doesn't look very nice, right? So, and in future when you saying that we want to send this graphs to some journals or something, then space is very precious, so you should not be wasting so much space here where unnecessary, there's no data as such. Okay, so we'll say format access. Okay, so we want this, we can, what was the starting value? 2.99. Okay, so we can start with the minimum of, let's say, 2.5. Okay, so now this looks much better than the previous one, okay, where it was only in one corner. Now the other thing was to find, so this is regarding the graph. So you need to take your points, mark properly. Don't over cramp it, because I can put here like 2.6, 2.7, but we don't want to do that. Okay, the spacing has to be good enough. Here also, if you don't want this, like you want 0.4 difference, then you can change this also. Okay, but I think this is fine with me. But here, now this interval is 0.02. Okay, so here, if you look at the major unit, okay, let's say it is fixed as, let's say, 0.3. Okay, so it has changed. So 0.03, 0.06, 0.9, 0.1. Is this clear for the graph part, plotting of it? The next part I'll explain to you, but this part of it. So the graph should be visually good enough. Having at a glance at it, it should give you the representation of your data with proper access. You should be able to read the graphs. There should not be any unnecessary things on the graph, because you're using graph as what? A visual aid. Yeah. There was some question.
So, so trend line basically mean we are drawing the line of best fit.
Yeah. Linear. When you're choosing a linear graph, yes.
Okay, sir.
Least square fit method. Okay, you can fit some other polynomial also. Okay, but since we know this is here, it's almost, see, if I don't take this point, this is fine. You can see that this is very linear, right? And because of this point only, and this line had to go like this. Suppose we don't plot this. Okay, which is that point.
So then the whole function will be changed.
So that's the first point, right? So now you see what is the regression value? Regression coefficient is 0.993. Fine. Okay.
Yes.
So, but we don't want to lose that point. So what we will do is, okay, now we'll go to data. Okay. So we'll go to a data. Now in data, you will have this get external data connection, sort, filter, data tools. Okay. So in data tools, what if analysis is there? Okay. So here, there are different things. I will use goal seek. Okay. What is my goal? My goal is to make this value 1. Okay. Fine.
We are not calculating that value.
Which value?
That one anywhere. It is calculated only in the graph.
Yeah. It's calculated only in the graph. Yeah.
But it has to be there in table somewhere, right?
And I put the value 1 here. Okay. To adjust this.
Okay.
Okay. So what I'll do is,
No, but that one has to
sorry.
that one has to be there in the calculation somewhere, right?
Set to value to, yeah, okay. Yeah. We'll have to set this value. R square. So there's a function that says square. Yeah. So this R square coefficient function is there. Okay. So unknown y's. These are my unknown y's. Okay. This is unknown x. Yeah. So this, yeah, 0.919, 0.9819. Okay. So set value of G63 to 1 we want to maximize by changing this cell, and let's say okay. Okay. We could see that it was doing the calculation. So if the value is 746, then I'll get a regression value of 0.9985. Okay. So this is what we get. But what has happened to this is that this values have changed. This graph has to be readjusted again. Okay. Format axis. So I will take it as 0.1. Okay, I can take it smaller also. Point. We can move this here. We can even change the starting value to 0.05 instead of 0. Okay. So you'll have to work on your graph so that it gives a good visual impact. I have few more values here if you would like. 0.05. Okay, so what we have done is that, so this R square is now 0.9989. This is almost the same. So we have used what if analysis to find out something from the graph. Otherwise, see, what would have happened if we don't have the what if analysis is that you'll have to keep changing this value manually and then try to figure out where you get the regression value 1. I'll tell you, it is going to be a very, very tedious task. Okay, now, and you could see that how many calculations it has done for you to arrive at the optimum value. Okay, so I had done this manually and I had got something 750. Okay, but then there is a difference of 4 degrees. Okay, which is huge. So,
Hello, sir.
yeah.
So with the same data, I'm getting something different.
What are you getting?
735.3. I've used the same data.
And what is the regression value you are getting?
Right now, I'm getting 0.9988.
Mm-hmm.
See, the fifth and sixth decimal places
Yeah,
in your case will be
maybe.
something like 32. Okay, whereas if you take 742 or so, it is going to be 56. So it is not very sensitive to fifth, sixth decimal place, and I think that is where that calculation precision can also be adjusted through Excel option. How many decimal places you want to be precise in auto calculations.
Yeah, because this is going up to, but so if I put 746 also, so it is still 0.9989 only. See, the whole thing here is that around 750, when I just look at this graph, okay, the value on the chart, then this is up to 4 decimal places, but here it takes much more to get you to that, and there's hardly any difference. After maybe 750, it would be changing in the 4th place or 5th place. The variation. Okay, so even if you put 750 here.
Yeah, one of the participants has messaged, Rohit has messaged that you go to 650, it is even better.
Huh?
Go to something like 650, it is even better. 611.
650.
611. So Rohit has done calculation with 611 and that
No,
goes
in 611
0.999.
the regression is 0.9973. So definitely you can see here it is 9973. So that variation is very, very, very small. That's what I'm saying, around that T0. Okay, I've done this. Even as I said, like 750, if I'm just going to look at this value which is there on the graph, which I have done initially, so I would stop when somewhere this value comes in, because it's like, there's a variation, there's a peak value I'm getting, and then that R value flattens out because I'm not able to see the variation in the next digits. Okay, so for the fifth digit variation is not visible to me, and therefore it's going to be a plateau. Okay, so either I can stop at the starting point of the plateau, okay, and then again there is a reversal. Okay, so 750 you see here, there is a slight difference here, but this value remains same. Even I think 760 would give us that. Okay, so yeah, this 0.9988. Okay, 889. Okay, so 10 degrees we changed this, and there was a 1-digit change in the fourth value, that is after the decimal point the fourth value changed by 1, so that there's hardly any change. So as I said, that value of R goes to going to 1, then it almost plateaus out. Okay, so I found that this is a better way of getting this. So this is
Sir, we can say that like although we are getting best fit like 0.9989 with this TGO, but like if we are changing TGO up to like 10 or 20, then also there is not much change in the R square value. Then we can say the value is less significant in our calculation. The TGO, like it is hardly affecting our R square up to like third decimal, fourth decimal. If you change like 100 by 100 or more, its value.
Yeah, so see, your TG0 value is not affected here, but then if you use this for further calculations, it makes a lot of difference. Okay, because this is like, as you said, it's an extrapolated value which is there. We are trying to calculate on the basis of fitting a linear regression. Okay. So the only assumption which we are going with is that it is a straight line.
Also, the number of data points are going to affect this, right? There are only 5 data points here, but suppose we had 10 data points, more precisely we could have calculated.
Yeah. But there's not much change. It would almost, because those points would be in between only.
So for these points, like for
Samples,
example,
no, you cannot go for this kind of samples out of this range. So for the heating rates have to be within this range. So that's a restriction on the collecting of the data also. So that if it is within this range, then it is interpolated. Yeah, outside this range, then yes.
So what does 20, 40, 60 represent here?
That are the heating rates. Okay, a sample is heated, cooled. That's a heating rate. Okay, per minute. That's a heating rate. So 20, 40, 60. Heating or cooling rate, you can take it. It's an average they give. Okay. So basically, a sample is heated at this rates per minute, and the TG is the glass transition temperatures. in metals. So that is what these values are. So this is the glass transition which is occurring at different heating rates. Okay.
This is the SI unit of heating rate, Kelvin per minute.
Temperature. This is like a no. The SI unit is it's Kelvin is the SI unit. Agreed, but it would be in seconds. But this data is per minute. This is the heating rate per minute. Okay, so 20 Kelvin per minute is the heating rate. This is basically a flow meter. Okay, heat flow meter. How much heat is to be passed so that the temperature changes. Okay, so these are called as DSC, differential scanning calorimeters we use. Okay, so let's go to add another graph. Okay, this graph is also the same. On the same data we have plotted this. Okay, so here it is ln beta by versus Tg. Okay, here it was 1 upon Tg minus T0. So here there is no Tg0 here. It is just ln of beta versus Tg. Okay. Now what we are interested here in this is basically the intercept. Okay. So I would like to know, okay, what would be the intercept of this. Okay. But what is this giving us? This is giving us what intercept? Now, if you can think of, this is starting from 825. Okay. So you can see that I have plotted the same, this thing. I have plotted ln beta versus Tg. Okay. So the same data is plotted from this table. Okay. So I just plot this. Now, if you look here, but this is going to be the y-intercept. Okay, when I put x is equal to 0, your y is equal to be going to be minus 71.363. Okay, but what I'm interested is not in the y-intercept. I'm interested in the x-intercept. Okay, so how do I get this? So one thing would be that you change the axis. Okay, so it's starting from 825. Okay, you start it from, let's say, 100 or so. Okay, that's too much. So the graph seems to be around some 700 or so. Let me change it to some format axis. Let us make it 700. Okay. Now I need this intercept here. So one way of looking at that would be is select the line. Okay, format the trend line. Okay. Now what you want is basically a forecast. Okay, forward or backward. Okay, so and how many periods? Okay, so let's say backward 20 periods. Okay, so it has come till here. So you're getting this. So you're basically trying to extrapolate this backwards, okay, so that you need to get an intercept. There are other ways of also finding that, but I was just looking at. So you can look at this with somewhere here, okay, but how do I know where it is? Then if you want to use a visual aid, then you will have to put on add the minor grids. Okay, so here you have, and this is 750, 60, 70, 80, 90. So it is somewhere between 790 and 800. Okay. So here you can find, yeah, I don't want to use regression now, but anyway, so when I do that, I'll get the x-intercept also. But you can, if you want further, you can have this grid lines. This is 50 and this is 10. Okay, so let us make it as 2. Then you will have to increase it. Okay, so we'll have to calculate, it would be around N93. Okay, so then you will have to just calculate it and look at it where the intercept would be, or you can do the calculation from here. Okay, put y is equal to 0 and then you can do the calculation. Okay, the other thing is that we can also use what is called as a line set. Okay. Okay, so we can use this function. So for that, I think I need to choose an array. Let me choose an array.
Two by two. 2 by 2 array.
Yeah, 2 by 2 array. Yes. And the 2 by 2 array. Okay, so the known y's. So the known y's are, this is a graph of ln. So ln beta is your y here, comma, the next array, that is this.
No, it is the other way, right?
No, it's ln beta versus
TG, right? 1 by
yeah. So the known y's are ln beta, the known x are this. Okay. So,
x is 1 by TG minus TGO, right?
no, for this
Okay,
graph it is,
okay, second graph.
for the previous graph it was. This graph is just ln beta versus TG. Okay, so what you can do is here in such cases when it's an array, instead of saying enter, you use Control Shift Enter. Okay, so use Control Shift Enter. Now it doesn't tell you what is what, but just looking at this, what has happened? It's giving the 7. Two by two, eh? Yeah. 3 values are there. No, I will not put that conditions. Okay, so constants hai. Okay. Yeah, b is set equal to 0. No, we don't want it to be set it to 0. The intercept is not. Okay. So true additional regression statistics if you want. If you don't want, you can say false to it. So it will not return those additional false if you say. Yeah. Control Shift Enter. So it has given me this value. Yeah, it has given me the same because I have said false here. So it is not returning any additional regression statistics. Okay, so if you say true here, so it will return me all this. Okay, so this first thing is nothing but the slope, as we can see from, which was this graph? Yeah. So 0.09, so that is, the slope is 0.89957. Here it is rounded off. This is the intercept, the y-intercept. Okay. This is the uncertainty. Okay. So this is the uncertainty in slope. Okay. So, and this is the uncertainty in the intercept. Okay. So normally we know that when we plot any graphs, okay, the uncertainty in the intercept is very, very large. Okay. So that's why normally people don't prefer using intercept. It's not a very good thing. If possible, we should avoid, because you can see that the uncertainty in slope is 0.003. Yeah, I agree the slope is also there. But here it would be plus minus 3. Okay, of minus 71 point. So this is the y-intercept. So it's going to be huge because it's ln beta plus minus 3. Okay, yeah, so it has written some additional statistics. Let me just pull it. I've chosen the array as 2 by 2. That's why it gave me only this much. But if I choose a 3 by 2, then the next value would be the regression value. Okay, so that is 0.9948, which I can see here. These are some values which we don't use. Okay, they are there. But what is important for us is the slope and the intercept. So finally, but line set will not give you the x-intercepts here. Okay, but when we go to regression, it will do the whole thing. Okay, so regression part I can. Okay, so let me do the regressional analysis also on this data. Okay, so here yesterday we asked you to do install this data analysis pack. Okay, and here we have the regression. Okay, I calculate on that. Okay, in this regression we'll input the y range, which is this. Okay, and we'll input the X range. Okay. See, here you can see that with what level of confidence you want to report. So this is the extended uncertainty we are talking of. So unless you tell it to confidence level 95% is the extended uncertainty. So whatever we just discussed there is here. So you can understand this now better. Okay, so you can put labels. Okay, now output options. So whether you want that on this page or a new page, a new workbook. Okay, so if you want the plots to be plotted, we have already plotted it, so we do not require the plot. Okay, so the residual plots also are there. So we'll restrict. So one point is that so you can understand this confidence level which we are discussing there. Okay, and yeah, so I'll take a new live book and let's see. Okay. Now it has gone to a new sheet and given me all the statistics here. This is a summary of the. So this is R, the R square. Okay. There's something called as adjusted R square. This is the standard error or the standard uncertainty. How many observations we have taken is 5. Okay. So significant figures. Okay. So coefficients, standard errors, t-test, intercepts. Okay. So this is this intercept of 71 point and the variable x variable value intercept. Okay, so coefficients. Okay, this is standard error in each one. Okay, so here you have the intercepts. So the point is that you can have different the whole analysis of it. We don't use much of it. We have significant figures. Okay, so residue is something which is not to be done here. So, but this is what is R square, your standard error, your observations, intercept. So this will be your, there are some probability functions significant. Okay, so I'll not go into that as such. So, one more thing is, we can stop today. Yeah, I can start with some matrices. Okay, now here you can see that I have two data points and a single x-axis but double y-axis. Okay, that's also known as the secondary axis. And we can also plot the error bars. Okay, so that's what we want to do here. Okay, so let's say insert the scatter. You have the XY scatter. Okay, select the data. Let's add, say just one series X, that is Y. Okay, so we have plotted this first one. Let me add one more. This would be a series 2, the X value from here, Y, now you can see that this graph is suppressed, and this is because both of them are on the same y-axis. Okay, now if you want to look them separately, what you can do is, okay, you can have, that was that.
On x-axis format, you will get that option. X-axis formatting.
This option. Where did I get it?
On y-axis only.
No y-axis. Okay, I just layouts. Yeah, it should come on the y-axis only. Format axis options. And dedicated, I didn't. Okay. Layouts. Yeah. Axis. Yeah. It's in the layouts. Yeah. Sorry. It's in the layouts, not in the design. Yeah. So your primary axis, this is the horizontal axis. Okay. And primary vertical axis. More primary axis options. Not this. I want this title. This is error bars. We can plot the error bars from here. Where did it go? Vertical axis. Vertical value. Let's do. And did anybody get where it is? This thing.
What are you looking for?
What are you checking, Shekhar?
Yeah, I want to say the secondary axis.
In the layout only.
Layout.
Just eat one graph. So you have one, only from that you can explain. Highlight only one of and one.
Did get it, but what's wrong with it? I'm not able to find it now. Chart layouts may.
Sir, it's in chart tools, design, combo plus
Chart layouts.
Chart layout, then
Yeah.
change chart type. Then there is
Yeah.
combo, and in that combo there is secondary axis option. So
Chart layouts, right?
means basically change chart type window is there. So all those XY scatter, radar, stock, surface, all those charts are there. In that there is option combo, and in that combo there is a tick mark option for secondary axis. So our usual chart change chart type window. You can access it through either chart tools or change chart type window by directly right clicking on our main sequence scatter chart.
Anyway, I'm not able to get it. I did plot it here.
Okay.
It will come back. Okay. So what we can do is plot the y-axis and the error bars. I'll show you the error bars in the layouts. Okay, so we can go to the error bars. There are no error bars here. Okay, error bars with standard errors. Okay, error bars with percentage and error bars with standard deviation. So we'll say error bar with standard this thing. So whether so it has both x and y. So if you are interested in both x and y, that's fine. Otherwise, we are okay. Only the x or the y. Okay, the error bars. So more error bar options we have here. Okay, in this, you want only the x. How do you want to represent it? Like this, or only the upper limit, or the lower limit, or the sideways? So you can choose from here. Okay, so you can choose how this is error bars. This thing from more error options. Okay, if you're not interested in the legs, let's say only the x bar, you can just delete this and then you will get only the y error bars. If you're interested in the x, okay, you're interested in both, you can keep both. Okay, so the only thing is that we couldn't find that y axis. Not, I forgot.
So it is there in change chart type option.
Okay, chart type. Yeah, it is there, but I'm not able to get it here. It's not there.
Sir, it is in design.
It is in the left corner in the design. Is there change
Yes,
chart
sir.
type?
First one.
There was an option named combo. It is not.
Yeah, I didn't have a combo, but yeah, I'll get it. Let's not waste time on that. I'll tell you how it is. So if you've got
Sir,
it, it is good.
how to introduce error bars? I don't have layout in my
Okay,
tab.
just click on the chart. Okay, anywhere on the chart.
Yes, sir.
Then you will have the design
Yes, sir.
on the top. And the next to it, you will have layout.
I don't have that.
Okay, so what are there? You have
After design, I have format. I have one thing called quick layout in the design.
Hello.
yeah. So go to that.
Hello.
Yeah.
Yeah.
If you click on chart, there is a plus sign appearing on right top corner. In that
Yeah.
plus sign, there is option of error bars.
Yeah, I got.
So
Okay, thank you.
okay. Save this. I'll just introduce a bit of matrices, how to write an array also. Okay. So, and then maybe next time we'll do the eigenvalues, finding eigenvalues. Okay. So suppose you have a matrix, let's say just a 2 by matrix, which is 3 by 2 minus 2, 1, okay, and then you have 2, 1, and 3. Okay. So you can name this array, you select all the cells of this, okay, and go to the name cell here, okay, and you can name it anything you like. Let's say we name it as M. Okay. So if I next time I don't have to select this array, if I just say equal to M, can you see this array is highlighted? Okay, so every time I don't have to use this array, I have given this array a name which is M. Okay, so it will take that value or that array in this consideration for calculation. So what will happen is when you're doing matrices and
Sir,
so on, yeah.
Sir, actually, I think my network was little fluctuated when you were that airing. Can you repeat it?
Okay. So what is that when you're doing metric multiplication, every time you have to choose an array and so on. So it will become tedious. So what we do is like, so you have some array which is here, right? You can select this whole array, go to the name cell, okay, on this corner. You can rename it like, let's say P, and then say it's not named. No, it's not allowing it. So you say it is M, then it will take it as M only, unless we delete everything. And okay, now it has gone. So what I'm doing is take this else. Oh, sorry. Paste it here. I want to name this array. Okay, just like we do it in matrices, we give some matrix A also. So you select this whole array. Okay, go to the name cell. Okay, give it some name, whatever you want. Okay, and henceforth when you want to use it, okay, as that array, you just say equal to M, and now you see that when I write this, this whole array is being selected. Is this clear?
Yes, sir. Thank you, sir.
Okay. Now similarly here, when I choose, so I want to find, I have given this as calling this as matrix A and calling this as matrix B. I select this whole array. Okay, go to the formula cell equal to. Okay, what is that I want to do? A into B. Okay, A. Okay, so what it will do? Should we write A into B?
Do you M multiply? You can use
I will
matrix
just
multiplication.
so the ordinary multiplication thing you should not do here. Okay, so you will have matrix multiplication. Okay, so you can have matrix inverse. Okay, you can have the matrix inverse. Okay, you can have the matrix determinant. Okay, so here we want to multiply the matrix, so you can just say matrix multiplication. So here we have to choose the array 1. So instead of choosing the whole array, we'll just write A, okay, comma the array B. So you see that when I just write A, the name, the whole array has been selected. Okay, the array B, okay, and then just say enter. Oh, enter will give you only one value. Okay, so what we should have done, you can go back, control shift enter. Sorry, I have to do it again. Select this whole thing equal to matrix multiplication, matrix A, matrix B, control shift enter. Okay, so when you are dealing with matrices or the arrays basically, okay, so don't use enter, you will use control shift and enter. Okay, so similarly you can do this also. What you will do? Yeah.
What does it do? Like control shift and enter. Practical.
It does the calculation for the whole array. So the command which is set for executing that is not enter, but it is control shift enter.
Okay, so for only matrices it is like that.
For array means we are calling this array as the matrices.
Any operation that involves multiple outputs in an array, it'll you have to do this.
Use control shift enter.
And then once it forms array, you can't delete individual elements.
Yeah.
So the whole array would be deleted.
For example, now if now for example, this which I wanted to rename it, you just saw, right? We renamed this M. Okay, even it will not allow you to rename it something else. Okay, so the individual values also, if you want to delete, it will not allow you to delete. Okay, so what you will have to do is select all of them. Okay, go to formulas space. Okay, you can make it empty. You want to get rid of it, otherwise that window will keep popping up saying that no, you cannot make changes to the array. Okay, so you will use control shift enter, and then that has gone. Okay, but if individually I want to delete something, it will not.
Okay. Thank you.
Because this is not
in the output array, it doesn't allow.
no,
like
this
that
array
y
also is, yeah, it has lost this thing. It has, yeah, here we can try that. See, you cannot change a part of the array when I try to delete this. So if I want to get rid of this, you'll have to select the whole array, delete everything, control shift enter. Okay, now that has gone. So you'll have to get rid of the whole thing. So okay.
Yes,
So
sir.
similarly here also you can just say what will we do? Equal to matrix multiplication. Yes. See, by mistake I pressed enter. Enter will not work. Okay, select it. Now you can say B, comma A. Enter will give me only one value again, because that is what we are used to. So that is, we can also find the determinant. What we'll say, equal to matrix determinant. Okay, so determinant of this is named as D. Let us choose D. So whenever I select D, this whole array is selected, right? So here if you enter, that is fine. Okay. Similarly, I can find inverse of T. I'm just showing this because we will use this in solving linear equations and finding eigenvalues. This is just for some practice. You have an array and how you could play out with that array. So equal to, what we will say, matrix inverse. We want an inverse here. Okay, so that's a matrix inverse. Okay, of what? You'll have to select the array or we'll just select D. Okay, and what we'll do? Not enter, control, shift, enter. So this is the inverse of D. How can you check it? You do matrix multiplication of inverse of D and see whether you're getting a unitary matrix. Okay. So this is something which we will require, but this is just for some practice. You can take some arrays and matrices, and next time we can solve some linear equations and find some eigenvalues. So assignment, I'll send it to Mahesh sir. I prepared some small assignment on standard deviation, standard errors calculation part. Anything else?
So when I'm using a determinant of matrix, it is showing me an error value.
Okay. What did you do?
Determinant of the matrix.
Okay. So let us calculate it here again. So let's say equal to, you're done equal to, you can
Yes,
just see
sir.
what I'm doing. Okay. So matrix determinant. Okay. Now you have to choose the array. Okay. Now this array, I have named it D. So if you have named it, given it a name, then that should be highlighted. Okay. If it is not, then you choose the array. Okay. Yeah. So choose the array. So it takes it as D only. Have you chosen the array properly?
Yes, sir.
Then what did you do? Just say enter.
Maybe the data which I have entered in the matrix, the determinant is coming out to be something else. That might be the cause.
Whatever it determinant, what is the value it is coming out? Only if it is 0, the inverse will not work out to be. That's a different issue.
But value
Some
is
value it
not
should
coming.
give.
It is showing value, hashtag value exponential.
Are you choosing your array properly?
Yes, sir, I've done it. It is being highlighted.
Just check in the array whether it is number type. If it is in text type or other, then it will create a problem. Just check the format those
Check the
cells.
values.
It is in general.
Convert it into numbers and do it.
Yes, 1 second, sir. Then also it is showing the same.
Probably okay. So what is
Okay,
this?
what do you do is
What is the determinant? Shekhar, you can try here itself. No, we
Yeah,
all
yeah.
can try. So
Yeah.
you give first row, second row, and third row. Let us see.
The only problem is, yeah, okay, you can try, but maybe there's some problem with the array. You just try it at another place. Maybe the cell, one of the cells has some other references set in it.
Okay, sir, I'm trying.
Now you can tell us the values also. We can work it out.
I'm just doing 1 minus 2, 2 and 4.
1 minus 2.
2 and 4. Oh,
Right?
no, 2 cross 2 matrix.
1 minus 2, what is it?
1 minus 2, and in the next row 2, 4.
2 and 4.
Yes.
It is giving me correctly 8.
Maybe some error, but I've done the same thing.
Yeah, getting 8.
And here you don't have to put shift enter because it's a single cell number.
No, yeah, I have put enter only.
Okay, what is the cell name you've given it? What is the name you've
Given
given it? Huh?
A,
A.
yeah.
Yeah. Okay, that should not be a problem because C works out to be a problem because C is assigned something else in Excel. So don't use C as a name. Okay. So that's why I also have skipped C. If you see that C is reserved for something else in C. So in Excel, so
At different place, it is giving me the correct answer.
now it is giving you, right?
Yeah.
Sir, I have a doubt.
Yeah.
Sir, I have done 2 by 2 matrix multiplication. If the multiplication is giving me a single value.
Okay, let's do it here only.
Shift enter you may not have pressed.
Shift
You have to, before you put the formula, select 4 cells.
Ah.
Then in the first cell you write the formula. Then shift,
So you tell us
control,
the
enter.
values. I'll do it and show again what is to be the procedure. Tell me the values.
I have done 32, 56.
32, 56.
Then in the next row 5 and 6.
5 and
6.
6.
The next matrix, first row 55 and 77.
55,
77.
27.
And second row 65 and 45.
55 and 45. Okay. So what will we get? Expect the answer to be a 2 by 2 matrix. Okay. So you select this array first. Okay. Then just go to the function cell, say equal to matrix multiplication. You just type MA. Okay. Choose the first array, comma. Choose the second array. Okay. You can close the bracket or also fine. Control, Shift, and Enter.
Okay. Okay. Got it. I was just taking just one cell that says
Yeah.
that was in one value.
Okay.
Thank you, sir.
Shekhar will end here and
Yeah, yes.
conclude and continue tomorrow.
Tomorrow it is. I didn't see the schedule.
Let us see the schedule, but we'll continue next time, right?
Yeah, so the part which is remaining supposed to do is solving simultaneous equations and some eigenvalue. So there we'll do some graphs also. So if you have any doubts, you can come that time.